This conference will now be recorded.
Hello everyone. In last class, we have seen some examples of nomenclature and also examples of cis-trans and EZ. And together we will now combine these two concepts, that is EZ isomerism as well as nomenclature. Both will apply together and we will see some examples. Once it is finished, next we'll start how we can prepare alkenes by following different types of methods and then physical properties of alkenes. So nomenclature with EZ isomerism. Here we have the first example. So this is the first example, and in this case we have bromo and we also have CC double bond. And in this nomenclature we also have to mention whether it is E or Z. So let's first try to understand whether it is E or Z, then we can choose the parent chain and the rest of the things, that is nomenclature. Okay, so here if we consider this double bond, suppose this is carbon number 1, this is carbon number 2, just for the sake of this EZ determination. I'm not numbering it for parent chain, I'm just numbering it for EZ determination. Now if you consider the left hand side carbon, that is carbon number 1, among bromine and methyl, obviously here bromine will get more priority. So I'm just encircling it. And if you look at the carbon number 2, you have ethyl group, you have methyl group. So ethyl group will be having more priority, and that is why now you can understand individually carbon 1 and 2. If you compare the high priority groups, they are on the opposite side. So that is why it must be E. So that is sure. Next, what you have to do, the parent chain we have to choose, and it will start from this side, because if you do so, the double bond will get least number. That is the first number, it is 1, 2, 3, 4 and 5. Let me erase this one so that you are not confused between these two. Now we will write the name. So it is E, and in the longest chain we have total 5 carbon. In 2 position we have bromo substituent, and we also have a methyl substituent at 3 position. Sorry, it is not methyl, it is hydrogen. Fine. Now if it is the case, then it will be 2 bromo. Double bond position in the parent chain is at 2 position. So that is why it will be 2 20. So this will be the name, E2 bromo 220. The next molecule will go to now hydrogen. Okay. Now we will choose the high priority groups. If you look at the carbon number, left hand side carbon, so this will be having more priority, and in the right hand side this will be having more priority. Now both the high priority groups, they are on the same side, so there is a chloro substitute. Now we will put numbers for deciding the parent chain, and it will start from this side, because if you do so, the double bond it will get number 3, but if you start from the right hand side, it will get higher number. So 1, 2, 3, 4, 5, 6, 7. So total 7 carbons we have. We have to start by writing Z. Now at 1 position we have chloro, and 3 position we have ethyl substituent. So this is one substituent, this is another substituent, but 1 chloro should be written first because of the alphabetical order. So 1 chloro, 3 ethyl, and in the parent chain total 7 carbon, position of double bond is 3. So that is why it will be 3 heptene. We'll go to the next molecule. Okay. Now choose first priority for carbon number. Suppose this is left hand side carbon, this is right hand side carbon. So obviously this is having more priority, and in the other side here this group will be having more priority. So high priority group, they are on the opposite side, so it should start with E. The next thing that we have to do, we have to put number for parent chain. So it will start from this side, because if you do so, the double bond position will be least. Now I'll move to this longest chain side. Don't move the other side where you will get 3 carbon, but here you will get 4 carbon. Now we have substituent at position 2. We have substituent at position 4. So at position 4 we have propyl group. At one position at 2 position we have methyl groups, right? 1, 2, 2, 3. So it will be 2. Methyl should be written before propyl, so that is why it is written first. 4 propyl. 2 methyl, 4 propyl. Longest chain total 8 carbon and position is 3. Double bond position is 3. So that is why it should be 3 octet. E2 methyl, 4 propyl, 3 octet. Okay. Comparison of physical properties of geometrical isomerism. Though we have seen geometrical isomerism, but if we specially talk about the physical properties based on the geometrical isomers, that means cis and trans, how we can differentiate on the basis of these physical properties. So melting point. The melting point of trans isomer, it will be higher than that of the corresponding cis isomer. Now the case is same. Remember, in case of alkane also we have seen when the structure is very symmetrical, the packing is very well. So same type of logic also applicable here. When you have the cis isomer, and if you compare it with trans isomer is obviously more symmetrical. Just take the case simplest. This is cis, right? Where you have 2 hydrogen on the same side. And this is trans. Now, if you compare their structure, you will be able to understand. Trans is more symmetrical, and as it is more symmetrical, so it will pack well in the crystal lattice. And that is the reason you can expect the melting point for trans isomer to be higher than the corresponding cis isomer. Corresponding cis isomer means you just have to keep the carbon number same. So that is why see these two in here also we have 2 carbon is double bonds. Total carbon is obviously 4. This is also 4. So keeping everything same, when you just change the cis and trans or E or Z, the more symmetrical one is trans or E, and that is why it will pack well in the crystal lattice, and to break the crystal lattice you have to provide more energy, so that is why melting point is high. The bond moments in the trans isomer are equal and opposite, so that is the reason that net dipole moment becomes 0. So as you can see, if you consider dipole moment, and when dipole moment is high, obviously polarity will be high. So if we compare polarity, if we want to check polarity for the trans isomer and the cis isomer, you just have to understand in which case dipole moment is high. So in trans isomer, these groups are opposite to each other, so as if they will cancel each other, and it is more applicable for trans because when it is trans, same groups are on the opposite side. If you consider E, it is not necessary that same groups will be on the opposite side. So it is more applicable for cis trans compared to EZ, right? So bond moments in the trans isomer are equal and opposite. So that is why net dipole moment will be 0. So you can expect more polarity in case of cis. What about the boiling point? The cis isomer have higher dipole moment that we have already seen, right? And in trans isomer, there is less dipole moment. Now, when we are talking about dipole moment, that means here you can expect more polarity. Polarity more in case of cis. Now, when there is more polarity, what happens? They are more polar and have strong intermolecular forces. Now, when we talk about boiling point, and if you want to know whether boiling point will be high or low, you just have to understand intermolecular force between molecules, because boiling point means what? From liquid phase you are moving to vapor state, right? And from liquid state the distance between two molecules, and in the vapor state the distance, if you compare, in the vapor state the distance is very high. So basically you have to increase the distance between two molecules. But if the interaction between two molecules is very strong, that means where intermolecular forces are very strong, you require more energy to separate the molecules, to increase the distance between the molecules. And that is the reason intermolecular forces we consider. And when there is more polarity in a molecule, intermolecular forces between two molecules will also be high because of this dipole-dipole interaction. And that is the reason compared to trans, now intermolecular force in Cs is high. So boiling point of Cs isomer, that will be high than the trans isomer. Okay. So by this logic, we can explain, we can compare boiling point of Cs and trans, but when it is melting point, you have to consider in which case you are having more symmetrical structure. So in that case, trans will be symmetrical and it will be aqueous crystal lattice, so it will be having higher melting point. So two different types of explanation. One is for melting point, another is for boiling point. In general, the solubility of a Cis isomer, it is higher than that of the corresponding trans isomer. And why it is so? Because in case of Cis isomer, we have already seen that the dipole-dipole interaction, it is high. So when there is dipole-dipole interaction is very high, the solubility, that is interaction with the solvent, will be good, and that is why solubility will be high. Though it is very general statement and it may vary with what type of solvent you have taken, right? And don't expect that we are talking about cis trans, that means it is alkene, and alkene is hydrocarbon. So obviously in water you cannot expect any solubility. So whatever solubility we are discussing, it is only for mainly for organic solvent, or you can say non-polar type of solvent, not aqueous solvent. So if you compare that, that is when you have same solvent, solubility of cis isomer, you can expect to be more. The molecules of cis isomer, it is less symmetrical and they are weakly held in the crystal lattice than the corresponding more symmetrical trans isomer. So same type of logic we have also seen when we have compared melting point. So here also we are talking about the same thing. It is less symmetrical. So the crystal, in the crystal lattice, the packing will not be very good. So that is why you can easily break it and you can make it soluble. If it is solid, then only this theory is applicable. And when you consider the first few members, they are obviously not solid. It is only applicable for solid alkene. When you have very higher member, when you consider, then only it is applicable. So more symmetrical trans isomer, it is less symmetrical trans isomer, cis isomer, which are weakly held in the crystal lattice. As a result, lesser amount of energy is required to break the crystal lattice of cis isomer. So when we compare solubility of solid alkene, one is cis, another one is trans. Then in case of cis, you can have a more solubility, okay? Because the packing is loose compared to trans isomer. But it is only for, we are talking about when it is solid alkene, not gaseous alkene or liquid. So alkene, next if we talk about preparation of alkene, alkenes can be prepared starting from alkynes, starting from alkyl halides or alcohols. So these three are the main substrate or starting material from which we will prepare alkene. Now the first one will be alkyne. This will be number, it will be A, this will be B, and it will be C. So total three separate, that is three separate discussion will be there. First we will see how we can prepare it starting from alkynes, that is C triple bond C. Then alkyl halide, that is RX, and then alcohol, that is ROH. Three different types of substrate. So when it is alkene, the catalytic hydrogenation we will do. Catalytic hydrogenation of alkynes. And you already know catalytic hydrogenation because we have already discussed same type of method under the heading of preparation of alkane. In that case, the starting material was alkene, but now you are preparing alkene. So your starting material should be alkyne, that is CC triple bond. So when CC double bond is the starting material, you are adding 2 hydrogen. Obviously, what you will get? You are adding 2 hydrogen. This double bond will be gone and now there is single bond, you will get alkane. But if you want to make CC double bond, you have to start from CC triple bond. Then only when you add two hydrogen, now one of the pi bond will be broken and there will be two new sigma bonds with hydrogen atoms. So that is why now we are starting from alkynes, so that after addition of two hydrogen atom to the triple bond, you can get alkene. Catalytic hydrogenation of alkynes to alkenes occurs at a faster rate compared to alkene to alkane. So what it means? When you are preparing alkane starting from alkene, which we have already learned, that situation, because there also we have done catalytic hydrogenation, and now you are doing alkyne to alkane preparation, alkyne to alkene preparation, same catalytic hydrogenation we are doing, but if you compare the rate, the first one is faster. But why it is so? Because when it is alkyne, it is linear in structure, and this type of reaction it occurs on the surface of the metal. So when there is linear type of structure like C triple bond, C, that is alkyne, then interaction with the substrate, that is detailed discussion is there, we are not going into that. Just remember it is because of its overall geometry that it is easier for it to do catalytic hydrogenation. During reduction of alkynes, except few cases obviously, there is a chance of formation of two types of alkene, either cis or trans, and that depends on what type of alkyne you have started with. Because if the alkyne is such, there is no chance of formation of cis and trans alkene, then this question does not arise. Because if you simply start from, suppose you have taken CH3C triple bond CH. Now here when you are doing hydrogenation, what you will be getting? You will be getting H double bond CH2. Now here cis trans, that question does not arise because here you have two different groups attached to carbon number 1, but in carbon number 2 you have same groups. So the question of cis trans doesn't arise. So only in few cases if you do not consider, in other cases cis trans alkene can be produced, and that depends on what type of reaction condition you have chosen for this hydrogenation. Though whenever we talk about hydrogenation, which is nothing but addition of two hydrogen atom, the first thing that comes in our mind is catalytic hydrogenation. Catalytic hydrogenation means when you use some hydrogen gas in presence of some metal catalyst, palladium, platinum, that is catalytic hydrogenation. But there are some other methods also that is possible. So depending on what type of condition you have used, you can have either cis alkene or trans alkene. So if your preference is only to make cis, then you have to choose that particular condition. If you only want to make trans, then there is another condition. If you do not want any selectivity, then you can simply do catalytic hydrogenation. So these are the three things as you can see here. If you simply do catalytic hydrogenation, which is this one, this is simply catalytic hydrogenation where full reduction is occurring. And that is actually another problem, because when you do catalytic hydrogenation under, I mean, when there is no control, it is not under control, what will happen? You just want to add two hydrogen, but instead you will end up with addition of 4 hydrogen. So as if we are making alkane, but that is not our purpose. So that is one of the problem with catalytic hydrogenation. You cannot stop the reaction up to alkene. Obviously, first there is formation of alkene like this, but when there is addition of only 1 mole of H2, but if there is another H2 is added, then we will end up with alkene, but that we do not want. Now see, there are two other conditions mentioned. If you use sodium metal in liquid ammonia, you can get not just partial reduction. Partial reduction means only 2 hydrogens are added and CC double bond is still there. And that actually we want. We do not want to prepare alkane. We are talking about preparation of alkane. We want partial reduction. We do not want full reduction. Now here not just partial reduction, but it is also anti-addition. 2 hydrogens are added to opposite side. and ultimately you are getting trans product. So this is the condition you have to use. There is another condition mentioned in blue color, that is also partial reduction, but now it is syn addition of hydrogen. And what is written here? It is written here hydrogen gas Lindlar's catalyst. Now what is Lindlar's catalyst? Lindlar catalyst is just like hydrogen, platinum, palladium or nickel, but there is slight difference, so that we can get partial reduction with syn addition, not full reduction. So what we will do, we will arrest the reaction at alkene stage and further reaction to get alkane like this, that will not happen. So we will stop the reaction at this position, next reaction will not happen. And that is why you have to use Lindlar catalyst, which is a modified version of catalytic hydrogenation. And the blue one and the green one that you are seeing, sodium in liquid ammonia, that is different, that is only for trans addition. So catalytic addition of alkyne in presence of PD supported over either calcium carbonate or BaSO4. So the metal is supported over this surface plus lead acetate plus partially poisoned, that is this whole thing is partially poisoned with either lead oxide or sulfur or quinoline, and this combination is called Lindlar catalyst. Try to understand the difference. When it is normal catalytic hydrogenation, it is hydrogen gas you have taken and you have taken some metal, simple, PT, PD or Ni. But when it is Lindlar catalyst, obviously hydrogen gas, but instead of taking pure PD, now PD is supported over either calcium carbonate or BaSO4. That is the first thing. The second thing is there is also presence of lead acetate. And the third thing is partially poisoned with any of these three substances, lead oxide or sulfur or quinoline. Quinoline is basically a compound like this. This is called quinoline. Just like pyridine, you have just one benzene ring extra. But whatever it is, this is the Lindlar catalyst combination. So why you should know it? Because suppose you are getting question based on Lindlar catalyst, some options are there and it is asking which one is Lindlar catalyst. So that is why we should know what is the composition of Lindlar catalyst. Now the next question is why we are doing poisoning. Poisoning means when you are using some catalyst and it is very reactive. Just like take the case of full reduction, what we use hydrogen on platinum palladium. But in this case, if you do not poison it with lead sulfide or quinoline or sulfur, it will show its full catalytic activity. And as a result, what is happening? You are now getting alkane, but that is your not desired product. You want to erase the reaction up to alkene stage, not further you want to go. So you have to decrease the catalytic activity. You have to control the catalytic activity. And that you can do by using some poison. The role of catalytic, it is a general term. Suppose I am saying catalytic poison. There are different types of catalytic poison. So this particular poison we are using for reducing the catalytic strength of this H2PD, PT or Ni. And that is why we are using some poison, so that it cannot show its full activity and the reaction is stopped at alkene and no further alkane we will get. Okay. And remember, this is always giving you cis alkene. And if it is reduced with sodium in liquid ammonia, all these reactions are reduction. Why? Because you are adding hydrogen. That is why all these reactions are reduction reaction. So in this case, sodium in liquid ammonia, and it is also having a name. It is a name reaction which is Birch reduction. In this case, trans alkene are the major products. And when it is Lindlar catalyst, cis is the major product. Okay. Now here you can see some examples. In the first case, we have taken H2 palladium on carbon, and in this case, it will give you full reduction product. So that is why you have started with alkyne, but you are getting alkane, but that we do not want. But if you want it, obviously you can use it. Suppose you want to prepare alkane directly from alkyne, then you can use it. Then in the next example, here we have CC triple bond, and both sides the R groups are not same. So there is a chance, there is a question of cis trans. Two types of possibilities are there, right? So here we are getting these two hydrogens added to opposite side, we are getting trans. And the third one is linear catalyst hydrogen. So both the hydrogen that will be added from the same side. So that is the reason now you are getting cis product. This is C. C means cis and T means trans. Okay. Now we will see the mechanism of Bart's reduction, because in the other two, if you consider linear catalyst H2PDC, they occurs on the surface. So there is some hydrogens, they are on the surface of some other substance, and now the alkyne is coming and these two hydrogens are added, and they are from the same side because these two hydrogens are on the surface of the remember some bed we use. Here it is PD on carbon. In linear catalyst, PD is present over CaCO3 or BaSO4. So there is some surface over which hydrogen is present, and the alkyne is approaching the hydrogens. Two hydrogens are added from the same side. But when it is Bart's reduction, it is not happening on the surface. It is undergoing some special type of mechanism. Look at this. Mechanism is interesting. And we were using sodium, which is a source of electron. So one electron will be present. See, just think about this CC triple bond. Suppose one bond I have broken, one pi bond. Instead, that is, instead of drawing the bond, I am just writing one electron on each carbon. Now, if there is extra electron from sodium, it will be two electrons. So that is why, see, it is single electron, but here it is two electron, and that is why we will say it is negative. And this type of species, it is called radical anion, because in the same species you have radical, you also have anion. So that is it is radical anion. And this is a less stable radical anion. It will generate minor product. And here the radical anion that we are having another possibility which is more stable, and this is major. Now why I am calling it more stable? Because in this case, these two electron, this is single electron, this is double electron, but still they are on the opposite side. So negative charge, when they are far from each other, that will create more stability. And that is why the second species, second radical anion is more stable compared to the first one. So obviously from the second species, that is from the more stable intermediate, you will get the major product. So finally, this negative charge over carbon, it is taking proton from ammonia. And don't be scared, I'm saying proton taking from ammonia, because normally what you know ammonia is base. It is always capturing proton. And if you are thinking how it can donate proton, now try to understand. It is relative thing. NH3 is basic, fine, but it is basic in presence of water. It can capture H from water. In presence of HCl, it can capture H plus from HCl. It can produce NH4 plus. But now it is in presence of C minus, which is even more basic than ammonia. So it is relative. Ammonia will be behaving as base. That depends on it is in the presence of what type of substance. If it is in presence of water or HCl, it is fine. It will be acting as base. But it is in presence of some negative charge over carbon, which will act as base. And as a result, ammonia is now relatively acidic. So that is why the C minus will capture here, NH2 minus will be produced, which is amide ion. Now you are simply having one electron over this carbon, left hand side carbon. Another electron will come from sodium, and you will get another negative charge over the other carbon. Again, it will take proton from ammonia. And finally, you are getting these two hydrogen opposite side. So this is major product, but from this also you will get some minor product. So this is the mechanism of Bart's reduction. Radical anion species is involved. Now one more thing we will see here, selectivity. Linear catalyst allows a chemist to reduce a triple bond in the presence of a double bond, but that you cannot do with normal catalytic hydrogenation. So see, same substrate we have taken. In one case you are using normal catalytic hydrogenation, but here you are using the modified version, which is linear catalyst. So this double bond is not intact in the product because H2PDC, it is so reactive, the catalyst is so strong, all the other double bonds will also be reduced. But we know linear catalyst will not do so. So see, this part is still intact. So that is why it can show some selectivity. Selectivity in the sense when your starting material is having double bond, triple bond together, and if you want to selectively convert the triple bond to cis-cc double bond, then you can use this one. Fine. So only reaction is happening in this section, but the other part is intact, right? So starting from alkyne, how we can prepare alkene, that part is over. The second substrate now we will choose is alkyl halide. Now this is also very interesting because now you will see some elimination reaction. Alkyl halide means what? There is alkyl group and there is X. Simply take a molecule CH3, CH2, Br. So this is alkyl halide. Now from this alkyl halide, what we will do? We will remove one hydrogen atom and one halogen atom. So it is basically the net removal of HBr. In general, you can say HX. And when you are doing so, you are getting this molecule. You can also take some other. Now, obviously, you cannot start from CH3Br because you are preparing alkene, and in alkene means C double bond C will be there. So, add minimum 2 carbon must be there. So, starting material, obviously, at least you have to start from CH3, CH2Br. Okay. So, here some elimination of HX. In general, you can write HX occurring from RX, and you are getting some double bond in the R part. Now, as HBr or HX, it may be HCl, is removed, you have to use some strong base because HBr is acidic in nature, HCl is acidic in nature. So, when you use some strong base like sodium ethoxide, NaOET, it is very strong base. Here, the basic part is OET. Or you can take concentrated alcoholic solution of KOH. Remember, it is not aqueous solution of KOH, it is alcoholic solution. Okay, because your starting material is alkyl halide, which will be better soluble in some alcohol, not water. So always alcoholic solution of KOH, and it will be undergoing dehydrohalogenation. Remember, dehydrogenation means what? Removal of 2 hydrogen. So when I am saying dehydrohalogenation, it is removal of 1 H, removal of 1 X. Together you can say dehydrohalogenation or removal of HX part, and you will get some alkene. This is the overall reaction. Now in this case, if I draw the molecule, instead of writing CH2, now I will write CH3, I will write it like this. Now with respect to Br, this carbon is alpha, this carbon is beta, right? So this is alpha carbon, this is beta carbon. So the hydrogen which is at beta, that hydrogen will be actually removed and you will get some double bond here. So this is the reaction. Okay. So each atom is removed from the beta carbon. So you can say beta hydrogen removal, and X will be removed from the alpha carbon. Because the carbon with which X is attached, we are calling it alpha carbon, and the next carbon we are calling it beta, and the next one will be gamma, like this. Now this reaction is also known as beta elimination because H is removed from beta. Now depending on what type of halogen atom you have, it may be F, Br, Cl, and depending on what type of alkyl group you have, this alkyl group may be simple chain, it may be branched, so it may vary. That will determine the rate of the reaction, and also depending on that, different types of mechanism is possible for elimination, but that is not part of this unit, because there is separate unit, in class 12, which is alkyl halide. So in that chapter you will get details of this elimination, that starting from alkyl halide there are different types of elimination mechanism, E1, E2, E1CB. So details you will get there in alkyl halide chapter, not here. Here we will just see the general mechanism of elimination. So rate of halogen, obviously I greater than Br than Cl. Fluorine is not very good leaving group. So here why I am saying leaving group, because this Br will be removed. So if this bond is very weak, that is carbon halogen bond, so you can easily break Ci bond compared to Cbr bond, because Ci bond distance is very high. You can easily break it. So that is the reason why you are getting this type of rate for halogen, and also the rate for alkyl groups, tertiary, secondary, primary. That means this part, when it is tertiary, the chance of elimination, the rate will be high compared to secondary, primary. Now the reason may be, when there is very that is high amount of branching present, tertiary carbon is present, and you are removing some small unit, you are removing some small molecule HX. Obviously in the molecule there will be some relief from steric hindrance. So when there is already some tertiary carbon present, you are removing some small part from this molecule, the reaction rate is high. So these are the rate for halogen and rate for alkyl group. Okay, so this one fine. Next, very important is Sedgwick rule and Hoffman rule. So Sedgwick rule, there are two types of spelling, both are used. It will give you more substituted alkyl. Now what I mean by more substituted alkyl? So when you will see example, it will be clear. But there is another type of product sometimes obtained, which is less substituted alkyl. And that is called Hoffman product, and that is based on Hoffman rule. So first we will see example where Sedgwick rule is operating and you are getting more substituted alkyl. Now this is applicable only when you have some alkyl halide where more than one type of beta hydrogen atoms are present. So what it means? Just go to the previous slide. In this case, we have taken the first example, CH3, CH2 Br. Now here, beta carbon, if you consider, I mean this one, you only have 3 beta hydrogen. So you just have one type of beta hydrogen, isn't it? Similarly, if I draw a molecule like this, Br, CH, CH2, CH3, CH2, CH3. So in this case also, if you consider the beta carbon, this is alpha carbon, this is beta carbon, this is beta carbon. Now both beta carbon, their environment is same, it is symmetrical molecule. So you cannot say there is two types of beta hydrogen, right? But suppose instead of this molecule, if I write CH3 here, now there is two different types of beta hydrogen, isn't it? Suppose this is beta 1 hydrogen, this is beta 2 type of hydrogen. Now there may be more than two types, there may be three types of beta hydrogen. That is also another possibility. Okay. So for symmetrical alkyl halide, which beta hydrogen will be removed? Obviously, if this beta is removed, what product you will get? You will get CH3, then CH, CH3. And if this beta 2 is removed, the molecule that you will get CH3, CH2, CH double bond CH2. So these two are not same. Now this is more substituted. This is less substituted. Because in this case, if you simply focus on CC double bond, on this side you have CH3 and H, on other side also you have CH3 and H. But here you have two hydrogen on one side, other side you have this large group and one H. So only one alkyl substituent is there. But in the previous case, you have two alkyl substituent surrounding this CC double. So that is why we are calling it more substituted. Lesser number of hydrogen attached to CC11C unit. That means it is more substituted. It is less substituted. That is the meaning of these two terms. Fine. So when you have more than one type of beta hydrogen, there is a chance of getting different types of alkene, and you have to understand which one you will get as major product. You will get more substituted alkene as the major product, and that is based on Set-Jeff rule. Look at this example. Here we have taken 2-bromopentane. In 2-bromopentane, this is alpha carbon because directly with this carbon bromine is attached. This is beta carbon. Suppose this is beta 1, this is beta 2. Now if hydrogen is removed from beta 1 in presence of some base, you will get CC double bond and it is pent 2 in. Look at this, it is written as major. This one is terminal double bond, pent 1 in, and this is minor, which you are getting by beta 2 hydrogen removal. So this is less substituted, more substituted is this one. Because in this case, if you look at CC double bond, you have 2 alkyl groups both sides and 2H, total 4 substituents surrounding CC double bond. But in this case, you have 2 hydrogen, one side, another side, 1 hydrogen and 1 alkyl group. So more alkyl groups are attached in CC double bond unit, more we can say that it is more substituted, right? Then, sorry, we'll take one more example to understand this Set-Jeff rule in a better way. So I will write one more molecule. This is halogen atom, and in this molecule you will see there will be total 3 different types of beta hydrogen. So first what we'll do, we will highlight the beta hydrogen, right? So this is beta 1 type of hydrogen. Suppose this is beta 2 type of hydrogen. This is beta 3 types of hydrogen. So these hydrogens are beta, isn't it? This is alpha. Now when you remove beta 1 type of hydrogen, what you get? For simplicity, I am writing it as Me2CH, CC double bond and ethyl group. You get this one. When you remove beta 2 type of hydrogen, what you get? You get and when you remove beta 3 hydrogen, sorry, this is beta 3. Now the double bond is this. Now, in which case, that is 3 possibilities we have already drawn, but you just have to understand which one will be the major one. See, when you remove this beta 3 type of hydrogen, that will actually give you the major product. Why? Because here, look at the substituent. You have total 4 alkyl substituent in the CC double bond. When it is beta 2 type of hydrogens you are removing, now there is total 3 alkyl substituent, 1 H. This will be the next measure. It is not first measure, it is the next measure. And when it is beta 1 type of hydrogen, you have 2 H substituent and 2 alkyl groups in the CC double bond. So this will give you minor product. Okay. So in this way, we can understand which one would be the major product. Now we'll try to understand how when we can get Hofmann product, because in the previous example, this one is actually Hofmann product, the minor one. But in this situation, you will not get Hofmann. Hofmann is a product we get which is less substituted. More substituted means more stable, but in Hofmann we get less substituted. But if you are thinking, then why we get less substituted? We still get less substituted, though it is unstable in some special cases. What are those special cases that you'll understand here? So here are the 4 points that you are seeing. The first point is bulky base. So in the previous case, we have not talked about any base. We are just focusing on the substrate. But suppose the base that you are using for removal of HX, if that base is a very bulky base, now what will happen? So here we have taken solvent TBUOH. TBUOH means Me3COH and TBUOK means what? 3-methyl substituted carbon, and then instead of this OH, now you have O minus K plus. Instead of potassium, you can also have Na, and the name will be TBUON. But whatever it is, the focus point is here. This is the base where you have to focus. And look at this base. This is so bulky, isn't it? I have written it in this way, so you are thinking how it is bulky. But if I write it like this, isn't it bulky? So when this bulky base will approach this substrate, there is different types of beta hydrogen. This is one type of beta hydrogen. This is another type of beta hydrogen. This is also same. These two are equivalent. This is different. So when this hydrogen is removed, you are getting more substituted product, which is cbse, but it is 28%, because to TBUO being bulky, it cannot approach the hydrogen. This hydrogen approach is difficult because with this hydrogen there is further branching, but hydrogen from these two methyl groups, it is easier to capture because there is less steric hindrance. Okay, this is the reason. But if you do the same reaction in NaOET, that is simpler base, now this is not sterically hindered base, now you can get cbse as the major product. Now this is one bulky base example. Another bulky base example is also there, which is called lithium diisopropyl amide. Suppose N is there, both side there is isopropyl group, and nitrogen total 3 valency, but one valence is missing, so that is it is negative, and positive charge is balanced by lithium salt. So it is lithium diisopropyl amide. Amide is NH2 minus, but instead of hydrogen, now you have two isopropyl groups. Now look at this base. This part is actually base. This is also very bulky base, isn't it? So in presence of TBUO minus or lithium diisopropyl amide, these are the special cases where we call it bulky base. You can get product which is more of Hofmann, less of cbse. So this is the first point. Now what about the second point, which is saying that gamma carbon is quaternary. Sometimes it may happen that you have some compound like this. Now in this case, how many different types of beta hydrogens is there? This is beta 1. Suppose this is beta 2. Now this carbon is gamma carbon, isn't it? And this gamma carbon is quaternary because it is attached to total 4 carbon. So it is quaternary carbon. Now the approach of the base to this position and approach of the base to D position, which one is easier? This one is easier, not this one. And when these hydrogens are will be removed by the base, the product that we will get is Me3C, CH2, CH, double bond CH2. So this part is intact, there is no change. But here CC double bond will be generated, and this is Hofmann product, isn't it? So when the substrate itself is very bulky, like gamma carbon quaternary, then also the chance of Hofmann increases. Okay. The next one is poor leaving group. Okay, before going to that, I will just want to mention that this one is not applicable in our case because we are discussing preparation of alkene starting from alkyl halide. And in alkyl halide, the leaving group means the X that we are removing. So this Br in that is alkyl halide, it is either AFCl, Br or R, but that cannot be bulky. But there are some other elimination reaction example where instead of halogen, some bulky groups are there. bulky living groups are there. So it is applicable only in those cases. So we are not discussing the last point, only we will discuss the third point, which is poor living group. Now, poor living group means what? We have already seen that I, Br and Cl in these three cases, though the rate order is like this, but in these three cases elimination we see. But fluorine is very poor living group. So that is why example with fluorine is not so common. So when you have fluorine in the compound, then you can get Hofmann product. Now, what is the reason behind it? To understand that, you have to take some fluorine substituted alkyl halide. So this is fluorine substituted alkyl halide. Okay. Now this is alpha carbon, this is beta carbon, this is also beta carbon. Suppose this is beta 1 and this is beta 2. So when it is beta 1, here you have this hydrogen, and in beta 2 you have this beta hydrogen, right? Now, as fluorine is very poor living group, so the breaking of CF bond, it will not occur very easily. So what will happen, as fluorine cannot remove very easily in presence of base, suppose I have taken OET minus, the base can easily capture these hydrogens. So when you are getting these CH bonds are broken by base, you can either get negative charge at this position when beta, this hydrogen is removed, or you can get negative charge at this position. So two types of carbon ions probabilities are there. Now which carbon ion is more stable? It is true that fluorine is close to it, so it can stabilize this negative charge and this one also. But which carbon ion is more stable? Remember, we have learned this thing about stability of carbon ion in unit 12. There we have seen when it is 1 degree like this is 1 degree. It will be more stable. Here, because of the plus I effect of these two methyl groups, it is further enhancing this negative charge, which is not increasing stability. So that is why this will not be stable, but this will be stable. As this is undergoing through carbonyl type of species, intermediate. Now this negative charge, it will make CC double bond, and now CF will be removed. Here, same thing also happened here, but the product that you will be getting from this side and the product that you will be getting from this side, these will be major. And remember, this is Hofmann product. This is not Hofmann product. This is ZJ product. This is less substituted product, and this will be the major product. Okay. So this is the reason when you have poor living group, the CF bond doesn't break easily, but compared to that, carbon ion generation can easily occur. And when you compare the carbon ion stability, it will, the major product you will get from that carbon ion which is more stable, and that is the reason we are getting Hofmann product. Okay. So these are the cases when we are getting Hofmann. Then the third method is starting from vicinal dihalide. Now this is also a type of alkyl halide, but it is not monoalkyl halide. It is there is a presence of total 2 halogens. So that is why it is dihalide, 1,2 dihalide. That means 2 halogens present at one position, 2 position. And these type of halides are also called vicinal dihalides. So this is one position, this is 2 position. In presence of Zn, there is net removal of Znx2. Here we have taken Br, so that is what is ZnBr2. And ultimately this is the side product, we are getting CC double. Now this is a dehalogenation process. Why? Because there is net removal of bromine diatomic molecule. So 2 halogen atoms are removed. So that is why the reaction is dehalogenation. Remember, dehydrohalogenation is removal of H and X, but here it is removal of X2. So that is what is dehalogenation. So now you can see the actual mechanism. We take zinc in presence of alcohol. We simply heat it. First, what happens? This Cr bond is converted to CH2. CH2Br bond is converted to CH2Zn, as if Zn is inserted in between C and Br. And in the second step, Now this CZN bond is broken and there is formation of CC double bond. This CBr bond is broken. So one Br from this side and ZnBr from the other side, together it produces ZnBr2. We can also take example like this where it is not symmetrical. So here also after removal of Zn, it is a net removal of ZnBr2. So you get propene as product. Fine. Now one more method is left, which is from alcohol, but we will not start today because we need detailed discussion related to this. So total 4 types of substrate, starting from C triple bond C, then this is A. Then in B we have seen how we can make it starting from Rx. Now another B is also there because this is Rx, this number C, that is also a type of B actually, but now there is 2R, 2x present in the with the alkyl group, right? So that is one to highlight. And number D will be starting from some alcohol, we can prepare L. So these are the main substrate that we use as starting material for the preparation of alkene. So we'll end the session here. Thank you for listening.